Hello and welcome to today's video. In today's video we are going to look at covalent bonding. So we are still looking at chemical bonding, but today we'll focus on covalent bonding. So what is covalent bonding? So this is a type of bonding in which nonmetals share electrons in order for them to become stable. And what does stability mean? So stability means having 8 or 2 electrons in the outermost shell. So what is so special about this type of bonding is that it only involves nonmetals. And what these nonmetals are going to do is that they are going to share electrons according to their valency number. So they share electrons according to their valency number or numbers. Then in terms of a visual representation, if we are looking at a single covalent bonding, we'll have something like this. So we have a nonmetal and then it will overlap with another nonmetal. Then this is where we'll call it the sharing center or the covalency center. So that is where the shared electrons are found. Let's quickly look at examples. Demonstrate covalent, which is also known as molecular bonding of each of the following using cross and dot diagram. Number 1, hydrogen molecule, which is H2. So when we look at the atomic structure of hydrogen, so H2, so we have 2 hydrogens here. So I will use different colors. So there's this hydrogen with its electron, then there is another hydrogen with its electron. So when you look at these two, they are both unstable. Why? Because they do not satisfy either the octet or the duplet. So what do? So they come together and they share the electrons according to their valency. So this hydrogen will overlap the outermost shell of this hydrogen will overlap with the hydrogen. So this one will put in that, and the other one will share this. And this will be a stable representation of each respective hydrogen. So the other hydrogen thinks it has the 2 electrons, and the other one also thinks it has the 2 electrons. And in this case, both are stable and they satisfy the duplet rule. They both think they have 2 electrons in their last shell. Let's look at another example similar to this for oxygen molecule, which is O2. So there's this oxygen with 2,6, and then there's another oxygen with 2,6. So the valence number for oxygen is 2, meaning each respective oxygen can share 2 electrons. So this guy will share those 2, this guy will also share those 2. So what will be the final structure? So the final structure is this oxygen with those 2 electrons inside, then the outermost shell will overlap with the outermost shell of the other oxygen. So it will put in to share those 2, the other one will also share those 2. Then you will have these as lone pairs outside, and these 2 there outside. So what is happening here is both oxygens satisfy the octet rule. They both think they have 8 electrons in the last shell. Let's look at another example. Let's look at a nitrogen molecule, which is N2. So one nitrogen is 2,5, and we have another nitrogen there thinking it has those 5. Then how do they become stable? So the question is, the valence number for nitrogen is 3, meaning each should share 3. So this one will share those 3, this one will equally share those 3. So the final structure is going to appear like this. So the outside will overlap. So this hydrogen will put in the 3, the other one will also put in 3. Then you have the remaining electrons. So those 2 will go outside, and both will satisfy the octet rule. Let's look at something different as example number 4. Water, H2O. So for these, what happens is the most electronegative element will be put in the middle. So we have 2 hydrogens. We have 2 hydrogens against 1 oxygen. Against 1 oxygen. So the valence number for oxygen is 2, meaning oxygen is supposed to gain. So this guy is supposed to gain 2. Then these guys, they can only gain 1 because the valence number is 1. So what happens in this case is the oxygen will be put at the center, and then hydrogen will overlap with the outermost shell. So this hydrogen will put in 1, then oxygen, because its valence number is 2, so it would put one there and another one there. Then we have the remainder of lone pairs, which are those which will be put outside. And in this case, both elements are stable. So this guy satisfies the duplet. It has 2 electrons in the outermost shell. This guy satisfies the octet because it has 8 electrons in the last shell. Let's look at the last example, which is carbon dioxide, CO2. So in this case, we have a carbon, which is 2,4. And then we have 2 oxygens, 1, 2, 2,6, and another oxygen, 2,6. So when we look at this, the valence number for carbon is 4, and the valence number for oxygen is 2. So carbon is going to share 4, oxygen is going to share 2. So in this case, carbon is put at the center, like that. Then the oxygen will overlap. So we have this oxygen here, and we'll have another oxygen this side. So carbon will share 4. But what will determine the number of electrons to share is oxygen. So in this case, what happens is the element with more number of atoms, or element with more atoms determine the electrons to share. So in this case, oxygen will determine. In the previous case, we had 2 hydrogens, 1 oxygen. So the hydrogen will decide the electrons to share. So that's a very important point to note. So in this case, the oxygen will decide. So oxygen will put 2 here, meaning carbon can also put 2. Oxygen will put 2 there, carbon will also put 2. Then for oxygen, you realize that when they share those, they'll remain with these 4. So those 4 will go outside. And in this case, both oxygen and carbon satisfy the octet rule. Then, one last important thing that I want to talk about is a pair of electrons. So, a pair of electrons represents a single bond. So where we see whether it's this pair or it's this pair or it's this pair. So this represents a single bond. Therefore, hydrogen can equally be represented as H. So there is a single bond. In the case of oxygen, we have this pair and that pair. So there are 2 bonds there. So oxygen can be presented as O double bond O. So this is another configuration that we can use to present these elements. If I come to nitrogen, So there are 6 there, meaning there are three bonds between nitrogen and nitrogen. So we can represent it like that. What does this mean in a case of water? So in a case of water, so you have hydrogen, you have oxygen, then you have hydrogen. So there's a single bond, there's a single bond. So you can represent water like that. Carbon dioxide, there's oxygen, there's carbon, there's oxygen. So there we have 2 pairs. So meaning there's a double bond. So this is very important when we especially looking at organic compounds. For example, I'm given methane. So methane is presented like this. So I can take this back to covalent bonds where I know that there's a carbon there which is bonded to hydrogen, 4 hydrogens like this. Then I know that there is that chemical bonding happening there. So this is just one example. In a case of where I'm looking at compound like ethene, where it's CH2. So I'm looking at a structure. I'm looking at a structure like this. There's hydrogen. So I can take this back to covalent bonding. So it's a carbon, obviously with those inside, bonded to another carbon. Then here I have 4 pairs of electrons. So it's 4 pairs of electrons there. Then I have the hydrogen there, hydrogen here, hydrogen there. So there we have that presentation. And when I count, I'll realize that all the elements in there are stable. Lastly, I can look at an example of a compound like this. Methanol. So I can take this compound back to covalent bonding. So it can be carbon 1, 2 bonded to oxygen, then this oxygen is bonded to hydrogen, then there's this hydrogen. So 1, 2, 1, 2, 1, 2, obviously there 1, 2, 1, 2. And for oxygen to be stable, obviously I have to put those lone pairs. So that's it about covalent bonding. See you in the next video. Thanks for watching.